switch to PowerPoint mode later, I thought I would first give you one illustrative example of how the Wheeler-Feynman theory works. That is why I have used the blackboard. And before I go to that, I want to mention a book which contains in detail the Wheeler-Feynman approach and its consequences, and that is a book which is in the library, but I will write down here the details. This is the reference where you will find it in one place. Apart from, of course, the classic papers which I referred to in 1945 and 49, they appeared in the Reviews of Modern Physics, and I will give some references later, and not this lecture, but in a later lecture. So, what I want to work out here is the following problem, that supposing you have a electric charge which you oscillate or make it accelerate, because we know from electromagnetic theory that an oscillating or accelerated electric charge radiates. So, the effect that you are looking for, you can actually verify by taking a general kind of problem in which you have got an accelerated charge. So, accelerator with the position is a, velocity is a dot, accelerator is a2 dot, like that. So, if you take the acceleration and in general you can Fourier analyze and take a particular Fourier component corresponding to omega as u naught e to the minus I omega t. Because everything is linear, if you can prove for this particular component, Fourier component, then you have proved it for a general charge, whatever it is that I am going to prove, which will become clear as time goes along. So, we do this Fourier decomposition. So, now you imagine that you have an electric charge sitting out here, and there are electric charges all over the universe, and you are dealing with a static Euclidean Minkowski universe. So, we are not yet getting to grips with cosmology per se. So, but we can see how Wheeler and Feynman got the answer by this particular example. So, when you have electric charges distributed, your own particular charge which you are talking about is here, that is at the center. And you can say that there is a cavity which contains vacuum around this charge, and then the next charges start distributing. So, any kind of charge distribution, you will always have this property. So, you take the radius of the vacuum sphere as r, and beyond this there is a medium with electric charges. So, we ascribe a refractive index n minus I k for the light or electromagnetic wave propagation. So, this is our input, and now when you move this charge, when you accelerate it, whatever wave is coming out is going to excite absorber particles. So, each particle is getting absorbed, is getting excited by the impulse that is coming from this particular electric charge. So, we will try to evaluate that in the following way, that first of all, supposing you go to a distance r from this point, where r is any value going from 0 to infinity, not 0, but r to infinity, then take a particular particle here, we call it a absorber particle, that is, it is going to play the role of absorbing whatever is emitted by this charge. So, imagine what the field here would have been from this electric charge if there were no other particles. Then this is the simplest solution you get, u naught E upon r sin theta. I will explain what sin theta is, and exponential I omega r minus t. So, this is the simple solution. You can take this as the original direction in which this component u naught was directed. So, this, and you take this angle as theta, any particular direction. Now, so then the result from ordinary electrodynamics tell you that if the charge is oscillating or accelerated in this direction, then in a direction theta you will find the field to be, electric field to be in this direction perpendicular to the radius vector. This is something you can verify from Maxwell's equations. So, if you took that u naught E upon r sin theta comes in because of that, and x this. So, this field is applied to the absorber particle. So, the absorber particle will start oscillating like this. Now, before we go further, we will modify this particular formula to take account of the fact that there is a refractive index. So, we have to do that. So, what happens is that this changes to an electric field equal to 2 E u naught sin theta. Something is the same, E u naught sin theta, this part is the same as for vacuum, but because now the electric field is not travelling through vacuum, but through a refractive index n minus I k, you have r into 1 plus n minus I k instead of just r here. So, we have this extra thing coming in. Then if you look at the e to the I omega part, you find that because of refractive index there is a phase factor. So, that phase factor will be like this, e to the I omega into n minus I k minus 1. So, anything different from 1 will add extra phase because of the refractive index. So, you get r minus big R. So, what happens altogether is you get this particular expression for this field here in this direction. So, now the absorber will respond to this, and if the electric charge is E, you can say that if electric field is E, the absorber will behave E upon m, P P of omega, where P of omega is a function which comes in this particular fashion. Now, this is the relationship of refractive index arising from a distribution of electric charges in a medium. So, this is also a standard formula. There is a P of omega which comes which may depend on the frequency. So, we just put this in here, and that same P of omega comes in the estimation of the response of the absorber particle to the electric field which was emitted by the charge. So, that is why this has come. So, now you have to do the following. You have got this electric charge moving, oscillating, or whatever the impulse is, it is responding to that. Now, that will produce a response back to the original point, original charge here, which you had started oscillating to estimate the whole effect. So, if you are looking at it here and this charge is oscillating here, so you find that the response, the electric field here will be in this direction, which is again perpendicular to this line. This is again using the same formula. Only thing is, first we took from here to here, now we are taking the effect back from there to here. Formula are similar, that is the same kind of 1 over r coming in. So, you do this calculation and then you say that this is happening to all the particles in the universe, and you hope that when you integrate over the whole thing, the thing will converge. If it diverges, then your whole project is doomed to failure. So, what happens is you have got this thing here, it is in this direction, and what you expect is that when you have summed over all directions, only this direction will survive, others will disappear, cancel each other by symmetry. So, we do this calculation, and here is what I have written, net response. So, now what is happening here is, first we got this E over m, the motion of the absorber particle, that produces again E upon 2 r sin theta e to the minus I omega r times the original field E. So, you substitute everything in here, and your integration is over all the 3 coordinates r theta phi, including this. This looks like an unknown factor, but it cancels out when you do the refractive index formula. So, when you do this, evaluate this integral, you get a finite answer, 2/3 I omega E u naught e to the minus I omega t. So, what you have done is, you have moved a charge, produced field at large distance. At large distance, any typical charge is responding, and because it is responding, its field is coming back to the original charge, and we have asked what is the contribution of that particle, and then you sum it over all directions. So, this will be the what is called the net response of the universe, because the universe is the rest of the particles. So, you have here, if you look at this thing here, you find that you have e to the minus I omega t into I omega u naught. So, it gives you something like a 2/3, there is probably a minus sign here. So, 2/3 E square A triple dot is, it has become E square because This is the electric field you calculated. If you want to know the force on the electric charge, you multiply by the electric field, electric charge itself. So, that is why that E becomes E square, and what you have got is this formula, that this is what is normally called the radiative reaction. You remember in my first talk I mentioned this was the formula Dirac had also used. So, that 2/3 E square, there is a power of C cube here, I have put C equal to 1, that is why it is not there. So, you got this result, and this result, if you actually do this calculation not at r equal to 0, that is we calculated the effect right at this point, but if you do it at a nearby point, that calculation can also be done, then you find that it comes as half of f retarded minus f advanced, where retarded and advanced fields are emitted by that original source charge. So, you get this formula verified, and if you go to the limit r equal to 0, this is what you are getting. So, in a sense it justifies your original expectation that if you wobble an electric charge, what is going on is that the whole of the universe is expanding, is responding, and because of that response you are getting the radiative reaction. And you will also notice that because in this whole calculation there is no infinity occurring at r equal to 0, because everything is well behaved, this integral or any force that you are calculating, and therefore you have in a sense avoided the self action problem which comes from field theory. So, you are able to explain this as the response of the universe coming from all over, and how this looks like in the neighborhood. Yesterday I had given some indication that if you take, this is our source charge here, and we take an absorber here, then the absorber will have a wave converging on this. Similarly, if you take an absorber here, it will be like this. So, you have all these absorbers on this side, and you will get wave fronts converging on the respective sources, and these wave fronts at large distance would be more or less flat. And so, when you sum over their effect, what it looks like is a round spherical wave front which is converging to this point here, the source point, and then what happens, each one is passing by. So, it goes through, and a little later if you examine, what you will see is these wave fronts are going out. So, you got the same sphere expanding. Now, what it means is you have got as a result of this response of the universe, first something which is converging on this charge, which would look to you like advanced field, and then it is emerging from the charge which would look like retarded field. So, these two are coming one after the other, and that is what you are seeing in this particular formula. So, the answer to the self action problem in the Wheeler-Feynman theory is that you are doing it, you are getting it not from the charge itself. There is no self action of the charge on itself, but it is coming because there is a universe present all around it. If there were no universe, if there were no electric charges at all, then this charge will not do anything. I mean, it won't go through this exercise. So, this is one thing that I want to emphasize before I go further. Now, if there is any doubt somebody has on what I have done, please, you can always interrupt me in the lectures, but yes.
So, these signals are propagating with the velocity of light.
Yes.
So, when you are, suppose I make a product one charge,
Yes.
so it will go up to some extent in some time.
Yes.
So, when you are integrating one from R, capital R to infinity,
Yes.
so this upper limit should be like C dt actually.
Mm-hmm.
And you should integrate over dt, like the distance I am more covering of the part of the universe. Like what I am saying is, suppose I am making a perturbation here now,
Mm-hmm.
that for a charge which is present, suppose at some very far away from me,
Yes.
to have an effect it will that much time. So
You are saying that if they are very far away, the effect will reach much later. No, this is not the case, because you are not traveling forward in time in the reaction, you are traveling backwards in time. You know, you have got here, from here to here. So, if supposing you had t equal to 0 here, so when this signal reaches here, it will be t equal to r plus c. It will be t equal to r, because r upon c, r is the time has gone. So, when you come to this, this charge will start responding, and that response is coming backward in time. It is like t plus r, not t minus r, because it is advanced. And so, it is coming back here exactly simultaneously as it started moving. See, so this is the major difference in ordinary ordinary causal argument and argument which involves a causality also. But as you see, the effect which is coming in advance, when you sum over all the particles, it kind of disappears. It does not show itself as a testable problem. So, that is the point here I want to make. Now, I had brought in thermodynamics yesterday, so I want to say something about why thermodynamics was brought in by Wheeler and Feynman. You see, this argument that we have used tells us that if you start with half retarded plus half advanced, this is the disturbance which each charge by itself lets out. Now, we said that to this we added a response of the universe which was f retarded minus f advanced. So, in the neighborhood of the electric charge, the total disturbance would be this much, and when you add this, what you get is f retarded. That means the advanced part has been cancelled out. So, when you do all this, when you do this calculation and come to this conclusion, everything seems logically right, but then you are surprised at the conclusion that you have reached, that you have got a time asymmetric, that is f retarded as the answer, f advanced has disappeared, although originally they were on equal footing. So, the question that Wheeler and Feynman asked, why is it happening? Why are we getting something in favor of retarded? That is what they wanted actually, to show why when you do any field theory and solve a problem in Maxwell's equation, you always say that we will reject retarded field because they are not, we reject the advanced fields because they are not consistent with causality. So, what is left is retarded, but that is by choice. You said you throw away the advanced field because they are not consistent with what we are explaining. in the case of action at a distance, you cannot throw away the advanced field, they have to disappear somehow, and that is how they have disappeared and you have got what you wanted apparently. So, Wheeler and Feynman then realized that they had missed out a possibility like this, that since everything is time symmetric, you can repeat the whole argument in which retarded is replaced by advanced and vice versa, because there is nothing to choose. So, when you do this, you will get this whole thing and the answer will be f advanced. So, so you are now saying both solutions are possible, retarded and advanced, and again the question is why, how do we choose? So, again if it is coming to your choice, then you have not done any progress over the Maxwellian approach. So, so what they did was they said that let us look at this in the way we have derived, and again this may have some relevance to your question again, that when you move this charge, the effect goes here and this starts moving, that is at a later stage. So, before it started moving, it was at rest, and we have put a condition that after it hits it, it starts moving and then it produces a response which you are calculating. Now, take the opposite solution, that where you are having everything advanced. Then what you are saying is that when this reaches a distance r, you say this is moving after it hit it, but that is not the case. Here it is before, that after becomes before, because we are talking of advanced fields. So, the advanced field that this charge is going to give, that advanced field was I mean this charge, for example, when the signal from here to here goes, it will start moving in advance, so that after the signal hits, it comes to rest. Or I want you to see the symmetry and think of it in a time opposite time running opposite direction. So, if you now say that absorber particles were all moving before, and as you made this oscillation in local charge, the effect was such that it hit the absorber particle and brought it to rest. Now, this seems very unlikely that you have particles moving in just such a way that the way you move here will bring it all to rest. So, they said why this is not so. Then they said this is because the thermodynamics tells us that it is a situation where you originally things were moving at random and then it came to rest, which became a systematic state. So, the entropy has gone down in this process, and if you want to have retarded advanced field to be consistent, you have to have situations where the entropy of the universe decreases after this experiment is done. And therefore, they said that it means you are going against the second law of thermodynamics, and therefore, this retarded field can be advanced field can be ruled out. So, their whole conclusion, which seemed logical enough at the time they did it, was that you make a symmetric theory, start a time symmetric theory, but use asymmetrical initial conditions, and those asymmetrical initial conditions will help you select the retarded solution as the right one and not the advanced field. So, this was the situation which where they left this particular work, and then they wanted to go for quantization. Yes?
Then the refractive index cancels out.
Sorry?
The refractive index
Mhm.
cancels out from the final result.
Huh.
So the value of the refractive index is used.
You mean the structure of the...
In this expression, use the refractive index.
Mhm.
Now that theta will not appear in the final result.
Yes, yes.
So it is independent of that.
You see, what has happened is you started with a fairly general situation, that the electric charge you are oscillating is oscillating in any general way, and this argument can be used there. So what is the...
But when we talk about refractive index,
Yes.
we have already just using the standard electrodynamics. That is.
Yeah, yeah.
So are we fair to use it now or at this stage?
No, the refractive index is used as a collective phenomenon. So many electric charges are present in a given volume and they are all interacting. So the effect is expressed by the refractive index, and that this formula n minus ik whole square, this is characteristic of refractive index due to many particles. So this is particle number density and this is omega. So this is what they used, the standard relationship of a refractive index to distribution of particles.
This does not assume that only retarded forces are there.
Yeah. This is purely within the electromagnetic framework. Do you want to bring in some non-electromagnetic forces to...
I mean, no, I mean, in general, I would have considered this to be a multi-body problem where you solve each electron and its charge, and it's a many-body problems.
Yes.
Which has been put into a simple form by refractive index.
Yes, yes.
So
this refractive index helps you to deal with a lot of electrons in a given volume. Instead of dealing with them individually, you try to... so in some kind of statistics is gone there. Yeah. Okay, so let me go a little bit further. So when this thing was looked at in the 1960s, I mean this was 1945 to 49, this is Wheeler-Feynman. Okay. Then 1962, there was a Canadian scientist, Hogarth, who was a student of McRae, Bill McRae, who is a British cosmologist in the 60s. And McRae had the idea, which of course his student carried out to completion, was the fact that all this calculation that we did was in a static universe. Now, if you are going to produce a realistic effect, your universe has to be realistic, and the realistic universe is expanding universe. So they said we should do this calculation in an expanding universe. So expanding universe means the following change. Let us take at the moment this standard Big Bang type universe, which starts with a big explosion and then starts cooling down, and its density becomes less and less. So if you are sending a signal into the future, this signal as it travels into the future gets redshifted. So it becomes a low frequency phenomenon. This is the, let us say this is the retarded field. This becomes redshifted. And similarly, supposing you sent an advance field which went into the past. Don't associate any time direction with these arrows. I am just distinguishing them from one from the other. So, if you had an advance field which was going into the past emitted today, it will be blue shifted. And so, it becomes a problem of high energy physics. What happens to such these quanta may become gamma ray quanta. So, the absorption properties that one is talking about will become different for future and past. In the static universe, this was not happening. Another thing is that if you look at the density of matter in the universe, the density of matter in the universe in the future will go on towards 0, and in the past it will go on towards infinity. So, when you are looking at interaction of what you call the onward signal, the original signal sent by the particle as we discussed here, then that signal when it hits the absorber particle will in the future case find the absorber with at a low frequency and low density, and in the past it will be the other way around. So, Hogarth and McRae, they decided to look at the problem in ab initio and see what cosmology gives. Now, see what happens when you start dealing with cosmology in this framework. So, Hogarth had said that you cannot achieve consistency with causality unless you use a cosmology to break the time symmetry. So, what Hogarth's argument was that using thermodynamics was not necessary because before you reach any thermodynamic argument, you first have to deal with a universe which is properly represented in terms as a expanding universe or whatever you feel the observers are telling you about. So, he made a distinction that there is a perfect future absorber and a perfect past absorber. Now, perfect future absorber, see, you take an electric charge and draw a light cone which goes into the future and anything that is lying in this part of the universe which lies in this will be future absorber. And similarly, you draw a past light cone and whatever is present in that light cone will be called the past absorber. And the condition that here that was happening was the following: perfect future absorber reacts to a stimulus like half of retarded minus advanced plus half of the time symmetric. Ts stands for time symmetric, half retarded plus half advanced, and that gave you retarded one. Now, in the past case, it is the reverse with a minus sign here and you get advanced. This is the thing I was discussing in the static universe, because in the static universe, whether you go in the future cone or past light cone, you get absorption which is perfect. So, you get both the retarded and advanced solutions as consistent. But in an expanding universe, that need not be the case, as you saw that something going in the future and something going in the past is encountering different type of physics. So, this is what we can say that differences between static and expanding world models. In the static model, density is constant. In the expanding model, the density goes as 1 over SQ, unless matter creation goes on in the universe. So, in 1960s, early 60s, the steady state model had considerable credibility because its nemesis, the microwave background, had not been discovered, or had been discovered, but people had not realized it existed. So, let us assume, take ourselves back to those those days. So, density is constant, and here density goes as 1 over s cube. And if matter creation like steady state was allowed, then density was constant in the past or future. No frequency shift in the static universe, advanced wave blue shifted, retarded waves red shifted. That difference I explained. Then absorption processes the same at all epochs in the static universe. Here they may be different for advanced waves because at past epochs you are dealing with high energy absorption processes, and future will be low energy ones. So, these will be different. If the future absorber is perfect, so is the past one, because of the symmetry in the static universe between past and future. This will happen, but here you cannot say beforehand. You have to examine each and every model and decide what should be the answer. So, this was done by Hogarth first, and later on Hoyle and I did the same work again for the following reason, that if you look at Hogarth's paper, it all looks very sound and all that, but when Feynman saw the paper, he got very upset, and he said, you have not done the problem correctly, because his argument was that Hogarth was using collisional damping as absorption process in the past and future, and collisional damping is a thermodynamic concept, which he was turning the sign backwards and so on. So, Feynman said, you have not got rid of thermodynamics, it has come back. See. So, it has to be redone. So, what we did was to stay away from anything of thermodynamic nature, and we said that if you take retarded solutions as consistent, then the radiative reaction will be in a certain direction time wise, and if the advanced fields are consistent, the radiative reaction sign changes, but that is purely electrodynamic effect, it is not a thermodynamic effect. So, we perhaps I should reminisce a little to tell you what had happened. Was in 1963 I was due to get my viva for PhD, and my two examiners were Herman Bondi and Dennis Sharma. They were both from Cambridge. No, Bondi was in London and Sharma was in Cambridge, and at that time Gould had organized a nature of time workshop in Cornell. So, he invited me and my two examiners and various other people, of course. Feynman was there, Wheeler was there. So, all these people had turned up. There were about 20 or 15 people sitting around the table, and our whole proceedings for 5 days was people giving a paper informally and responding to what the others wanted to say. So, at that time Hogarth was there, he gave his talk, and Feynman was very critical. That was expected, but when my turn came, I had been forewarned what to avoid. So, I kept away from thermodynamics altogether, and Feynman, although he asked questions, they were more or less I would say harmless questions. But before this conference started, Gold had made a announcement that he was going to tape record everything that was said in that discussion. He said that will be a good proceeding for the conference because it was informal. So Feynman on that erupted and said, if that is the case, I am quitting, I am not taking part in this conference. So everybody was surprised, why is he saying that? So his argument was that, to put it in his own words, that I can make any silly remark during the discussion and not worry about it. But if you are going to put it in print, then I have to go and defend what I said, and I don't want to do that. So this went back and forth for a while until they arrived at a via media. So Feynman's name doesn't appear in the whole proceedings, but he is replaced by one Mr. X. You see, and if you are clever enough, you will find out who X is. But nowhere does it say it was Feynman, or people who were talking about some remark that Feynman make, they would just say X. I mean, it was put down as X in the proceeding. So that is how it happened. And anyway, when I gave my talk, Feynman made some statements, but they were generally innocuous. Then that afternoon, evening, Bondi said, we have to hold the viva for my examination. So at that time, they had got permission from the university to hold it outside the premises of Cambridge. Normally they want viva to be in the university campus. So Cambridge University said that so long as none of you are claiming travel expenses, we will allow you to hold it in Cornell. So it was supposed to be held in Cornell. So Bondi said, tomorrow we will meet after lunch. So I said, the lunch is over at 2 o'clock and seminar, this conference starts at 2:30. So will you get enough time to ask questions? He said, you don't worry about it, that is our worry. And so after lunch, when everybody disappeared for short break, they asked me each 2 or 3 questions, and they said, that's it, viva is over. Because yesterday you gave a talk and there were a lot of people asking questions, so that takes care of the viva. So that is how I remember this 1963 year. So what I want to do tomorrow, no, not tomorrow, the next lecture, is bring these cosmological implications more closely into the picture and see what they suggest. There are various results written here. These are different cosmological models. So, and models that were known in those days with some slight renaming. So, here Big Bang plus inflation, the inflation was not known, but the implication is you have omega equal to 1, that is the cosmology. Friedman plus 1 curvature, Friedman minus 1 curvature, Brans-Dicke had variable gravitational constant affecting cosmology. Dirac had large numbers hypothesis which gave a different cosmological model. There was a steady state, and then later on I put quasi-steady state because recently Kaustubh Deshpande had shown that it works in a certain way. So I will come to that my talk on next Monday. I think I will stop here. Any modulo, any questions from any of you?
questions? Okay, if not, let's thank Professor Narlikar.
Thank you.
And the next lecture is on 21st.